in the milestone, I did put one, I mean, the milestone literally is one of the tasks we did before, right? So here's a screen for the milestone. Yeah, so one of the tasks we did before. So what we ask you to do is to design a digital filter without any kind of existing filter from SP2, from external filter design package, just everything in the code, be able to run the code, apply the filter to a polluted audio and restore the audio signal. So that's basically is. And in addition to that, there's kind of a breakdown requirement you can look at. In addition to that, you also need to display. So as part of the result, you also need to display 10 audio samples in their native data format. So people ask, what is native data format? So I'm going to explain that. If we review the early lab, okay, so here is the lab we did at the very early of this module, which is first, or I think it's the second lab, which is to do with reading audio file from a WAV file. Okay, so in this case, we are actually read a WAV file. WAV file follows the audio standard as written in this red book, CD standard. Yeah, CD standard. Digital audio standard is the first, is the CD standard. So what it basically says is using 16 bits to encoding any audio data samples. Okay, so in here, the paragraph here in the third page, it says in the PCM format, it's called PCM format, postcode modulation format, audio file. So 16-bit means you have 16 position, 1 and zeros, to representing the amplitude of any sample. If you using 16 bits data representing a data with both negative and positive, the range of that representation is from minus 32,768 to positive 32,767. So that's the range. So the pure, if you just representing the positive side of 16-bit, you probably, the range will be 0 to 65,535. Yeah, so that's the range if you just representing positive. What I ask you to do is to be able to read audio file and display the actual sample in this data format. That's native data format. That's how it is stored in the CD, how it is stored in the data file. So how are we going to do that in practice? So let's go. Okay, so within MATLAB, we read audio data using, for example, signal fs equal to audio read, yeah? And then we put the file name there. So if you have a file name called piano middle C in your directory, so you can simply copy paste here, and then you can run the data. You can run this line of code. Audio, sorry, this is the wrong format. Needs to be parentheses bracket. Yeah, just a typo. Okay, so we try again. Now it works. All right, so now if you look at the signal you have been read into the memory, it's not the format as it described in the theory a moment ago. So this is the signal. You can see the signal is not, we all know signal is between -1 to 1. Why it is format is in theory, it is between minus 32,000 something to positive 32,000 something, is because the audio read, when you read the data, it will convert or normalize the audio data from the native format into this called float point, double precision float point format. The reason doing that is because for CD quality, 16 bits. So in this case, the PCM 16 bits is converted to double float point. Yeah, so I hope you studied this from other programming course. Float point is using this decimal point to represent the data. The reason being, the float point has much higher dynamic range than the digital representation, the native format, which is 16-bit. 16-bit about 96 dB, where the float point could, in theory, double precision 64 bits, float point in theory about 1000 dB dynamic range. You can do loads of audio processing without introducing any processing noise. So the requirement in the Moodle is to look at the data in the native format. All right, so we can give you an example. So if I'm going to read the signal in native format, I don't want to read a sampling frequency again, so I just do a sig native equal to audio read. And in audio read, this function actually support read into a data into the variable with specific data type. Okay, so if I search native format, so if you read audio data using native, then return the data in the data range corresponding to data type native or double. This can include the input algorithm in previous syntaxes. Basically, that means it will read the original data format rather than convert into float point, to give you opportunity to observe how the data actually written in the audio file or the disks. So here I give you example to read compressed, which is loosely compressed FLAC audio data in the native format. But like almost all the DAW, when you're processing audio, they always convert to float point already. So this native format is really try to let you understand how the native works. Okay. You see, if you request the audio data in the native format, then the view data type will have a data type as integer. So we can use this format in our example here to see what happens. So what we need to do is really just give another example, another parameter within the after the audio file, just using common and native here. So we just run this again. Okay. Let's do a CLC. So we now, after this, we will say, if you type whos, you will display all the data here. So signal is when we read the signal, which is automatically converting to double. So the class is double. When we actually read native, the information is written into a sig native variable, and you can see now the class is int 16. So if then we look at this signal, Okay, so we display that data, all the data signal in the screen now. I mean, certainly it's quite a large of number of data displayed. So you can see they all integer value. So this is actually how the data be encoded in the data file. So you need to basically say in my assessment, you also need to display a 10 random value or audio sample or top 10 magnitude sample, whatever you choose, display on the screen. It depends the requirement. Okay, so that's basically is the requirement of this 10 audio samples from in their native data format.